Welcome to lecture 19. So today we will talk about more general codes which are called the universal codes. But before that there was one doubt regarding the coding of Markov sources. So let me talk about clarify that how the inequality how the source coding theorem we can say for the Markov source work. So assume a Markov source. So we discussed the Huffman encoding scheme for the Markov source, but I did not discuss the generalized the information theoretic format. So what we can do for Markov source, we know that there is something called the entropy rate. So entropy rate we can write in the asymptotic way. So entropy rate is basically in the limit, say it tends to infinity. So we can write it in two ways. One is the regular definition, that is h of x1 to xn when n tends to infinity. Another way is the asymptotic conditional entropy. So that is xn given the past, and we know that for Markov source the entire past does not matter, so only the previous state matters. So that is equal to limit n tends to infinity h of xn given xn minus 1. So any, like, it depends only on the previous state, previous random variable at time n is n minus 1. Okay, so here the notation we have taken is that previous state is written as suppose s, and new state is say x. Then this same limit can be written as limit h of x given s, where s is the previous state. Even in the book the same notation has been taken. Okay, now what is h x given s? This is when, like, I should not write limit anymore. This is assuming that the steady state has been reached, so there is no more n. So this is where the steady state is reached. So what is h x given s? It is essentially, just a minute. So this is essentially summation of h x given one state into probability of that state, where this q is the steady state distribution. So this is for all s. So this qs is the steady state distribution of the Markov chain, PMF of the Markov chain. You know how to compute this QS. This we have discussed while talking about Markov chain earlier. Okay, so what we can do, so assuming some instantiation of the previous state, assuming s is equal to some small s, then that is now a real number, that is some instantiation, then what will be the corresponding entropy? The entropy will be h of x given that value s. So this is what, and this is this you can compute from the corresponding PMF of the corresponding row. So for the Markov chain, these are the previous state s, these are the next state x. So this is some value s. So for that, this is the corresponding row, that is a PMF. So these are basically PS1, PS2, etc., PSM, etc. The sum is equal to 1. So for that row you have the Kraft inequality. So you can compute for that row, you can compute like L si I can write, where previous state is s is equal to basically minus log of psi, and for the ceiling. So using this we can do the encoding, and this should satisfy the source coding theorem, that is h x given s is less than equal to the minimum when previous state is s, and this is equal to h x given s plus 1. This I can write. Now multiply So this one is basically, this hx given s is basically coming from these probabilities. Okay, so that we know. Now what we can do, we can multiply with every element here with this steady state probability, which is qs. Then we can see that qs x hx given small s is less than equal to qs l min s, where previous state is s. This is only less than h of x given s into qs plus qs, and this is true for all s. Now you can sum it over all s. So if you sum it over all s, what you will get, the first term is basically the conditional entropy or entropy rate. Conditional entropy corresponding to the previous random variable, which is same as the entropy rate. What is this? This is the L min of the overall, where the previous state is s, and that occurs with this steady state probability, which is qs, and this is again the entropy rate, plus this is one. So that is the source coding theorem for the Markov source. And using this method, in the regular way, you can generate the Kraft inequality, and you can get the encoding, so which we discussed already earlier. Okay, so that is all about Markov chain. Now we will move towards the more general universal encoding, which was done by Zeeb and Lempel, and that encoding we will do next. It is called the Zeeb-Lempel encoding. If you are interested, I can share the original paper with you, that is with me. Let us get the idea. The idea behind Zeeb-Lempel encoding is that there are two rationale. So why we need universal encoding? What are the problems of Huffman or Kraft encodings? So the problem is, one problem of Huffman encoding is the following: the problem of buffer, problem of Huffman, we can say. Huffman or any fixed to variable code encoding, fixed to variable encoding, is a problem of buffer. We know that suppose the input bit symbol streams are coming at a particular rate. So this is your encoder, and symbol input bit stream is symbol stream is coming. So which is say A1, A4, A7, etc. These are coming at a particular rate. So that rate can be one symbol per TS unit of time, TS second, we can say. Then what do I expect? I expect the output to have also a kind of bit rate. So asymptotically the bit rate is fine, which is coming towards the entropy or entropy rate. However, the problem is, suppose A1 is mapped to 0 and A7 is mapped to say 1, 1, 1, 1, 1. So here you are generating 1 bit, here you are generating 5 bit. It is fine that you are expecting that this will occur much more time, much more likely A1 with high probability, A7 is with very low probability. So on the average length is minimized. That is fine. But in this encoder, what you have to do, you have to since you are emitting the bits at a fixed rate, you should have some buffer which will store all the other bits. So suppose you have some entropy rate which is hx is equal to say 1.2 bits per second, okay, or bits per symbol, I should say, bits per symbol. So then that means that the time you are providing here, you are expecting to push 1.2 bits in that duration, whatever duration you are giving. So when you are sending 1 bit, that 1 bit can like move forward pretty easily, and you are gaining 0.2 like that 0.2 bits in terms of time. But when these 5 bits are coming, whatever less likely it is, you need to have some buffer which will store these bits, and they will emit 1.2 every time symbol. So you need a big buffer, and suppose this A7 occurs twice back to back. Whatever low probability that is, there is a possibility, right? So you have to have a buffer size of 10 bits. And this is not only 5, this can be really big. So when you have larger symbols, you have seen that how the binary tree grows in a Huffman encoding. So it can be really big. So the lower the probability is, the bigger the code length is. So the amount of the size of the buffer which has to be required at the encoder, that is really big. But whether that entire buffer is used all the time, not really. It will be used only when that very low probability event happens. All the other time the buffer is remaining unused. So that is one problem of this Huffman or fixed to variable encoding, where for every fixed symbol you are assigning a variable length of coding. So it will be better if we can encode using some kind of fixed length encode, fixed length code. So that will be much better. However, can we use our information theoretic results for generating such a code? So this was one of the objective of going towards universal encoding, but this is not the main. The main thing is, of course, that is not about only Huffman. All other previous code is knowledge about the statistics, knowledge about the PMF of the source. PMF for say discrete memoryless source, and transition probability matrix of the Markov source. So knowledge of the statistics, this is one of the most critical stuff, because unless you know that, you cannot generate the Huffman or Kraft kind of encoding scheme. And if you want to estimate them from the data itself, so initial phase when you are training the encoder, the statistics, how are you going to code those symbols? So are you going for a fixed length encoding? So that will what if the statistics changes with time? The PMF or the transition probability matrix, that changes with time, albeit it can be of a large amount of time. Still, if it changes, we need to have some adaptive mechanism by which we can do the encoding. So these are the rationale behind this universal kind of encoding, which will not be dependent on the PMF or TPM exactly. Rather, we will more rely on the asymptotic equipartition property of information theory. So we will assume that there is some stationarity at least for some large time. So even if the statistics changes, we assume that the statistics, the corresponding probabilities, that remain same for a long duration of time, and after that it is allowed to change. So no issue. So this universal encoding, this is a variable to variable encoding. Okay. Before going into describing the algorithm, let me give you the basic rationale of this Ziblampel encoding. This will be a variable to variable encoding. The rationale is the following. Let us take one small example. Suppose you have two symbols in your alphabet, okay, A and B, obviously, and so fixed encoding is basically map A to 0 and B to 1, that's it. But suppose the probabilities are not close to 0.5. The probabilities are, say, PA is equal to, say, 10 to the power minus 6, and B is equal to, say, 1 minus 10 to the power minus 6. So what is the entropy? So it is kind of deterministic system. You can see that it is close to 0 and this is close to 1. So if you draw the entropy will be, we know the curve of the entropy for a Bernoulli random variable. This is when P is equal to 0, this is a P, and this is say Q, and this is say P is equal to 1. So for both P is equal to 0 and P is equal to 1, the entropy value is 0. So when 10 to the power minus 6, it will be very close to this point. So the entropy is very less. You can compute it, right? So Hx you compute 10 to the power minus 6 log 10 to the power 6 plus 1 minus 10 to the power minus 6 log 1 by 1 minus 10 to the power minus 6. So you can see that this value is large, but it is multiplied with a very small value, and this is like close to log 1, so which is 0. So it is very close to 0. It is very small. Now how do I encode? So I expect that I should encode it close to Hx. So that is what my Kraft inequality, etc., the source coding theorem, etc., says, that my objective will be to encode using close to Hx. But how do I encode it? So if I specify, say for the higher probability thing 1 bit, and for the lower probability thing, like why do you go for 2, 3, 4 bits? Not required. The minimum value is 1 bit. So if you provide 1 bit and 1 bit, the mean length will be 1 bit only. But your Hx is much less than 1 bit. So how to exploit this small entropy value? So the idea is as follows. We will not encode A and B. Rather, we will do some kind of run length encoding. So we can use run length encoding. That is, you have the sequence, okay? A is occurring with very low probability and B is occurring with very high probability. So it's like a long list of B's, and then one A appears, then again a long list of B appears. So two occurrence of A simultaneously is having a very low probability, but suppose that also happens. But these B's are occurring at a very the sequence of B is very high. You can see the probability is say 1 minus 10 to the power minus 6. So it is close to 1. And these are happening say once in every million occurrences. A. Okay. So what will I do? I will not encode A and B separately at all. Rather, I will encode the size of the sequence of B. That is like the run length. And I will encode that number. So this entire sequence, which is of size say 10 to the power 6 or 10 to the power 7, suppose. This is the length of 10 to the power 7. So if you go by regular encoding, what you will do? You will do every A and B with 1 bit, 0 and 1. So it will take 10 to the power 7 bits to encode the entire scheme. Okay. What I will do? I will not use like that. Rather, I will use that occurrence of A that is like a parsing, that is like a comma, full stop, etc. After that, there is a long sequence of B, and I count that how many number of times the symbol B appears. So suppose it appears at 10 to the power 1.2 into 10 to the power 6 times. That is the number. So encode this using binary. So how many number of bits will be required to encode this number? Log of that number. So log of 1.2 into 10 to the power 6, suppose. This many numbers. Then again A appears. So you encode this, then A appears, then the next sequence of B again happens. You encode that number. So suppose this B sequence is number n1, n2, here say 0, here say n3, etc. So what you encode? You encode the number n1 by log n1 bit plus the number n2 using log n2 bits plus the number n0 say using log 0 bits, etc. Plus log n3 bits, etc. Okay. So only these numbers will encode the entire string. So the entire thing will be basically a log of the number. So you are decreasing the size drastically. However, there is one problem, that what will be the size of n1, n2, etc. Like I'm writing it log n1 in an imprecise way. So if n1 is say 4, how to encode? Using binary. If n is say 10 to the power 6, how to encode? If n is say 10 to the power 8, How to encode? So what should be my number of bits to represent that number? So if I go for a fixed length encoding here, so I have to take a very long, like very large number as my binary encoding maximum. But again, that maximum is not statistically viable because there is a probability that it can exceed that number. So we cannot really use a fixed length binary encoding. Rather, we can take some unary binary encoding which will not require any fixed length of the bit stream. Rather, this is a prefix free method by which I expect the number to start at 1, the MSB will be 1, and whatever be the length in that of that binary stream, I will precede it with n-1 number of zeros. So such that it becomes a unique representation and it will take 2 into log n1, that many number of bits. So I am giving you this scheme, this unary binary encoding scheme, and this will be useful for our ZBLEMP as well. So what is my policy? My policy is that if the number, so let me write down the numbers, the integers, and these are the codes. So let me write first the binary code and then I'll write the unary binary code. And you will understand that why it is prefix free. So suppose the number is 0. So if the number is 0, I will use just the binary code of say actually 0 does not matter because 0 is nothing. That probability is very low. So I'll start with I'll start with 1. So it is basically for the natural numbers, I can say. 0 I am excluding. So start with 1. So binary code of that is 1 and unary binary code is also 1. Let us take the number 2. The corresponding binary code is 1 0. I will precede it with another 0. So I will write 0 1 0. Let us take the number 3. So this is 1 1. I precede it with a 0. So it will be 0 1 1. Let us take 4. 4 is 1 0 0. So I will precede it with 2 zeros. 0 0 1 0 0. You see? So the order is, if it is 1, so log 1 is 0. So it is around like 2 log n minus 1. So many bits will be required. Bits per number. You check it. 5. 1 0 1. 0 0 1 0 1. 6. 1 1 0. 0 0 1 1 0. 7. 1 1 1. 0 0 1 1 1. If I take 8, it will be 1 0 0 0. In that case, I will proceed with 3 zeros. 1 0 0 0. So this is 8. Log 8 is 3. 2 into 3 is 6. Minus 1 5. Yeah, it will not be this way. It will be the floor plus 1. That means number of bits. So 8 is equal to 3, n is equal to 8. So log n is equal to 3. So 2 into 3 is 6 plus 1 7. So 7 number. For 7, log n floor is 2. So 2 into 2 is 4 plus 1 5. Yeah, this is the actual number of bits which will be required. For 9, 1 0 0 1, it will be 0 0 0 1 0 0 1. So on and so forth. So if the number is say n is equal to 256, you will need not 8 bits, rather you will need 17 bits to represent it uniquely. Okay. So you are multiplying by this factor 2 for the representation, of course, but when you see that the number of the sequence number that is not limited to any maximal value and that changes with time, then this will be a much better encoding scheme. And this encoding scheme is a prefix tree. Let us grow the binary tree, you will understand immediately. So this unary binary code is a prefix free code. So I can start growing the code from here. So suppose this side is 1, so 1 is 1, this is 0, this side is 1, 0 1, so this is 0 1 0, that is 2, 0 1 1 is 3, this side is 0, this side is 1, this side is 0, this one it can be 0 1, then it can be 0 1. So 0 0 1 0 0 is 4, 0 0 1 0 1 is 5, 0 0 1 1 0 is 6, 0 0 1 1 1 is 7. For 8 you have to move further, 0 1, then 0 1 0 1 0 1. So this will be 0 0 0 1 0 0 0, that will be 8, this will be 9, this will be 10, this will be 11, this will be 12, this will be 13, this will be 14, this will be 15. You see, 0 0 0 1 1 1 1, this is 15. So you can grow this tree in this way as long as you want. There is no restriction, and this grows to infinity. So this can like basically encode the entire natural number line, all the numbers, uniquely prefix free way, only at the cost of that multiplied 2. That's it. But when we are talking about asymptotic length and all, that 2 is not a big expense for our numbers when you are doing logarithm of the number anyway. So earlier it was only the number into the number of bits per symbol. So this run length encoding actually compresses the number of bits required to a significant number. It is making it logarithm. Okay. So now with this idea, we are generalizing towards the zib-lempel code, so which takes the idea of the run length encoding. So what it does, so there are two algorithms which like the first one is called the Lempel-Zib 77 and another is called the Lempel-Zib 78. So these are the two main algorithms which are developed in 1977 and 1978. So this took the approach of a sliding window, which I will discuss, and this sliding window technique is used actually in Windows, Microsoft Windows. So for those WinRAR kind of applications, and this takes some adaptive dictionary approach, which is mostly used in Unix. Okay, so whatever compression you see in computer files, in text files, image files, the initial WinRAR kind of compression, that they are basically this universal encoding compression. Okay, so I'll talk about this LZ77. This is the like one prototype encoder. There are many modifications of these initial algorithms later on, but I'm not going into all the details. That is not required. You should understand the crux of the idea that how we can generalize run length encoding for any symbol, for any alphabet. So let us take the alphabet to be this. So this is having the symbols, and the cardinality is M. Okay. So what we are seeing, so your discrete source means after like source followed by sampling and quantization. So this is your discrete source which is emitting these symbols. So these symbols I am writing as some xn, which means the sequence starting from x1 to xn. Actually I can write it x1n. So 1 is the starting point, n is the ending point. So in this way I can generalize it to some xmn. It means the sequence, I can write in the first bracket. So this is the sequence starting from xm to xm plus 1 ... to xn. So when n is greater than m. So this is the compact writing of the sequence from xm to xn by this x subscript m superscript n. Okay, so what it does, the symbols are coming out. So what it will do, it will keep, so take a number w, which is a large number. So this is a large number. How large, what is the dimension, we'll talk later. So take a number w, then keep a sliding window of size w. So this is a sliding window of size w. That means for time, the time is basically w into ts, if ts is for every symbol, so such that w symbols are contained within that sliding window. Okay, so if I start from say x1, this sliding window will go up to xw, and I can say that this entire sequence is basically x1w. That is what it is. Okay, it can start from any some other point as well. If you start from say okay, we will show you how to slide it. So let us put a pointer p. That pointer, I will say that this is basically the last symbol of the sliding window. So to begin with, we will say that p is equal to w. So this is the initial condition. I start with x is equal to x1 and such that the first sliding window ends at w. So p is equal to w. Then I will increase p accordingly as we move forward. Okay. So what we will do, we will not encode every symbol. Rather, after xw, after xp, so p is the pointer, after xp, say take the symbol xp plus 1. So we start at symbol xp plus 1 and move forward and move to say xp plus n. So what does that mean? That means that suppose this is your sliding window which is there, and this is your xp. Up to this, it is within the sliding window. Okay, so it starts at xp minus w plus 1, say. That is the starting point, this is the ending point. Now you have the next symbol which is xp plus 1. This is xp plus 1, and I move forward up to xp plus n. So this is a sequence of n symbols. These symbols compactly I can write as x p plus 1 to p plus n. That is how I am writing the sequence. Okay, so that entire sequence which is of length n, okay, which is of length n, that sequence I will start searching within this sliding window, and my intuition is that sequence has already happened. Okay, this sequence is not a surprise, it has already happened within this sliding window when p is this w is large, this size is w. So I will search the sequence xp plus 1 to xp plus n, sorry, xp plus 1 to p plus n, this sequence in the sliding window, and I will search it from this side. Okay, such that suppose after searching I find that okay, this exact sequence of size length that appeared within this interval and that appeared here. So this is your you slide it up to u units and you get it here. So this symbol is say x p plus 1 minus u, where you have got it, you have got the match, and this symbol is xp plus 1 p plus n minus u, say p plus n minus u. This is where you get the match. So you start sliding back, you start the searching operation, searching backwards, and get the match, get the first match, say. There can be more matches here, but I will take only the first match. First match to be xp plus 1 minus u to xp plus n minus u. That is my match. Okay. So these two sequence, xp plus 1 to p plus n and xp plus 1 minus u to xp plus n minus u. These two matches exactly. Then encode two numbers, n and u. Just encode these two numbers. You don't have to encode the symbols within this sequence of size n. Just encoding these two numbers, which are natural numbers, that is good enough. Ensure that n is greater than 1. If n is equal to 1, then it does not make sense, because that means this sequence is exactly same as just the previous sequence. That does not make sense. At least it has to be greater than or equal to 2. Then this method is meaningful. And if it is equal to 1, I will just use the fixed length encoding for transmitting that particular symbol. Okay. How will I do encoding of these two numbers n and u? For n, since this n can be really small and it can be really big, so I don't know the range of n. N can be really big, and this particular sequence can overflow this xp also. It is not restricted within this window length. So the starting point will be within this window length, but the ending point can go towards this. So there can be overlap between this symbol and that symbol. I'll take one example such that you can see. So n can be of any length. So for any length, and it can be really small and really big, so it will be best to encode using unary binary encoding, as we have just discussed. For u is restricted to w. So u starts from 1, so this is like 1, and this is like w. So u is less than w, always less than equal to w. So for that you can use log w number of bits. Log w number of bits. And for this, how many number of required? 2 log n plus 1. So many number of bits are required. So for every chunk of symbols, xp plus 1 to xp plus n, you need 2 log n plus 1 plus log w number of bits to represent that chunk. And once that encoding is done, then you move your pointer from xp. So you make p to p plus n. So that will be your new pointer. You move xp to p plus n, xp minus w plus 1 to xp plus n minus w plus 1. So it also moves. So that will be your new sliding window. And then again proceed forward. So then go to the searching operation again. So if I write this to be step 2, so the initial condition is say step 1, then step 2, this is say step 3, so this is say step 4, step 5, go to step 2 and run ad infinitum. So as long as the symbols are there, you move forward. So this is the algorithm, but it seems a little abstract at this point of time, unless I give you some example that how it works, and then also the motivation that how it does the compression. Okay, let me show you. So the methodology by which we can show that how that information theory is like working here, and how you can have compression, how asymptotic equipartition property is actually helping. Okay, so why, we can say why it works. You see that if this is a this source is a stationary source. Stationary source is without losing any generality, because your discrete memoryless source is also a stationary source. So I am taking a stationary source. If it is discrete memoryless source, no harm. The same argument will follow. So suppose this is the entropy rate. So what AEP says? AEP says, in a in a vague way I am stating this, not the precise inequalities, but you understand. So there are typically two to the power n h xs strings, symbol strings of length n. So if you take the symbols and if you take like length of n symbols, so some x p to p plus n, p plus 1 to p plus n, this is a sequence of n symbols. So if this is typical symbol, so there will be 2 to the power n hx given as so many strings will be available in the typical set. So in that so many strings will be available, and the probability, corresponding probability will be 2 to the power minus h n hx given as. This will be the probability of occurrence of such strings. Okay, so you see that if w is small, the probability that you will get the typical strings of length n is less. So it depends on how long you are taking the w. So if your w, for what I am expecting, so this is a string of n, so you have to give 2 to the power n h number of strings to appear within that w. So if that w is of the order of n into 2 to the power n h x by s, if w is of this order, then you can expect that within that length of w, so this is suppose w and w is this, you expect that within this length all these sequences, all the typical sequences, they appear. So why this? Because when after this p, this is the pointer p, this is say p plus 1 minus w, after this pointer p, I expect one typical sequence to appear always. That is what the asymptotic equipartition property says, that whenever some n string appears, it will be a typical sequence with high probability. So I expect, when I am expecting some n sequence to appear there, I also expect that that n sequence has already happened within the size of w. So the probability of getting that sequence within this interval is large, close to 1. So then the corresponding method that you expect that this particular sequence has already happened within that window of w, that is large. So this will work. So you need the length of w is of this order. Okay. If so, then see, take logarithm both side. So logarithm of w will be close to log n plus nh x given s, right? So you can say that what is n? So n is of the order of log w minus log n divided by h x given s. And if you are working on n, you can ignore this log n. Log n is much small compared to n. So if n is say 1024, log n is 10. So for 1024, you can ignore this 10. Okay, or it can be even more, right? Then the log n by n goes to 0. So this is close to say log w by h x given s. Okay. Then if so, then for n symbols, how many bits you are using? For n symbols, how many bits you are using? You are using 2 log n plus 1 plus log w. So for n symbols, you are using number of bits used is equal to log w plus 2 log n plus 1. So many number of bits. So what is the bit rate, asymptotic bit rate? Bit per symbol, I can say. So I can write R in bits per symbol is this divided by n. So log w plus 2 log n plus 1 divided by n. So as n is large, this log n by n is close to 0, 1 by n is also 0. So it will be approximately log w by n. And you can take w to be 2 to the power some number format, so it will be log w strictly. So what is log w by n? You see, log w by n is approximately hx given as. So this method, and using this asymptotic equipartition property, using the understanding that the sequence of n will appear with high probability, you can see that the bits per symbol or the rate that is coming close to the entropy bound. So the corresponding run length encoding I have discussed over there, which you cannot do using Huffman or Kraft method, this one, even there you can approach the entropy, this run length or Zibel-Lempel method. Okay. Let me show you one example that how actually this is working, because this seems a little difficult otherwise. How exactly the algorithm works. Example. Let us take the alphabet to be A, B, C, D. And another thing, it does not require any knowledge of probability, that you have seen already. It does not require any knowledge of probability. So I'm not assuming any entropy, any PMF of this alphabet. Okay, only the occurrence, and the occurrence is happening according to the asymptotic equipartition property. So only the string, the sample function, you can say, the sample sequence, you can say, that is good enough. So assume some sample sequence of this form. Oh, okay. One thing I forgot to mention, that is this Zibel-Lempel algorithm. This will work. This will work. The initial length of W, the initial sliding window, when there is no prior information, you encode everything using fixed length encoding. So each symbol you encode using log W, but this will happen only once. So in the asymptotic case, that initial preamble, it will not harm much. Okay, so the initial part will be n into it will take total W into log m number of bits. So for those W symbols, you are using fixed length, but when you are like moving forward, that one thing which is only the preamble, that will die down, that will not have any effect in this asymptotic behavior. Okay. So I am starting with this. Suppose A, B, C, A, D, A, C, B, D, A, C, A, B, C, D, A. Assume H, X given as the entropy rate to be 1.2 bits per symbol. Okay, this is 1.2 bits, and now A, D C A A B S C D A B C A D A. I'm taking a really large set. So B C A B C D A C A B C D A D A C B B C C D A B C D, etc. Suppose this is the thing, and let us assume that n is equal to, say, typically 4. Okay, it can be 3, it can be 5, etc., but typically 4. So if so, then I have shown you that the W, let us take W to be around 2 to the power nh x, actually this. So if that is the number, it is basically 4 into 2 to the power 4 into 1.2, suppose 1.25, then it will be a complete number. So 4 into 1.25 is 5, so that is 35, 32 into 4 is 128. Okay, so W is 120. I have to take even longer. You take some sequence. Okay, suppose there is something even prior to this, so you take some sequence of 128. The sliding window is of size 128. So this will be a good exercise if you try in MATLAB coding in a computer. That will be even easier, but I'm showing you on pen and paper. So suppose up to this, so this is your first sliding window, so this is your x1, this is your xp. Your p is equal to W, which is 128. Okay, right? Then what you do, you start from here. You see that for every n, so you run a for loop, so n is equal to 1, n is equal to 2, n is equal to 3, etc. So as long as you can go, so you see that AA, can you see any match here? You are seeing match here already. AAB, can you see? Yes, you are getting match here. ABC, you are seeing match. D, you are seeing match. A, you are seeing match. No more. Here you stop, because this is C, this is A. Okay, you can go behind, and if you can get for like bigger n, so you can see that are you getting any bigger match prior to this. So AAB here you are getting, but it is not followed by C, so this will not work. AB you are getting here, ABC you are getting, D you are getting, A you are getting. So A, B, C, D, A. Here it was C, so you could not match, but here you are going for A, you are seeing that, so it is a little bigger. No more. So this is the biggest match you can get. So what you are taking, from xp plus 1 to 1 2 3 4 5 6 7, xp plus 1 plus 7. That is the sequence of n is equal to 7. 1 2 3 4 5 6 7. So how do you encode n? You will encode n using 0 0 1 1 1, using 5 bits. That is the encoding of n. How will you encode u? So what is u? U is 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 27 28 29 30 31. So u is your 31. And that how can you encode? So you are encoding using log W. So what is log W? So log W is 7. Log W is 7. So you can encode this using 7 bits. So the encoding is 111100. That is 31, isn't it? So what you will do, this entire sequence of 7 symbols, this will be encoded using first n followed by u. So 00111 0011111. So this is your encoding of like these 7 symbols. 7 symbols. Okay. So how many bits are required? 12. So 12 bits for 7 symbols. As these 7 symbols, if this grows, you will get even better representation. Now up to x1 to xp, the initial phase, that you have to encode using regular encoding, which is the fixed length encoding, that you can do using 2 bits per symbol. So you can do that for 2 bits per symbol. You can map it like a is equal to 00, b is equal to 01, c is equal to 10, d is equal to 11, in that way. So you finish that up to this, so up to 128 symbols, and then this is your first sequence, which is these 7 symbols. Once that is obtained, you move xp to this point. This will be the next xp. Then you start searching, and subsequently this will also move 7 units. So that will be your sliding window. Then you start searching that what will be the maximal length which you have already got matched within the W sliding window. And if you get some 7 is equal to say 8 or 9, and that you are getting matched somewhere, so again you take those 2 numbers n and you encode. N using unary binary, you encode using log W, and then you use like this. First you encode the n, second you encode the u. How do you know what is n? Search for the number of zeros. If there are 2 zeros, then go 3 bits after that. If you are getting 3 zeros, go 4 bit after that. So whatever number of zeros you are obtaining, go 1 bit more, and this will be your number that you can get from the unary binary tree. From here you can get that what number is that, and after that you search 7 bits, because you know that you are basically finding out the u, which is essentially the pointer, the amount the address moves, so that you can encode using 7 bits, log of 128, isn't it? So this way it moves. I can give you one assignment. Let me frame the assignment today itself, that regarding, because this is one assignment which can be done using a computer. There are some problems in digital communication which will not be done using computer, which are very much circuit specific. Those we will do in the laboratory. So once you come back, we will run our lab. But the experiments which can be done using a computer, like this universal encoding, I will use it here. So today I am framing the problem. I will give that to you. You try that out. You will understand how it is working and what kind of compression you are getting. So if you can write this, you will know that you know how to write WinRAR code. So you are writing basically a piece of your operating system, you can say. So with this, I am stopping today. In the next class, I will be starting. Okay, I will take one small class on this second law of thermodynamics that I have promised already in the Google Classroom. Somebody asked some. So that I will discuss that how the different distributions, for example, uniform distribution, normal distribution, exponential distribution, everything arises by maximizing differential entropy or entropy. Okay, so that thing I will discuss. Then we will go towards modulation. So up to what we have completed, so remember our original block diagram. So this will be our source, this is our sampling, quantization, source coding. So we are done up to this point. We compressed, we removed the redundancy. So now I have a bit stream, a sequence of zeros and ones. So next we have to understand what is a channel and how we can send this bit stream through the channel. So we will take two approaches. One is the baseband channel approach, which is a like one level abstraction, one level upward abstraction, and then we can go for the real channel. So wait for the next lecture tomorrow. Till then, bye.